This UCSD TV program is a presentation of University of California Television for educational and non-commercial use only.
If nature has Higgs in store for us, then we would definitely begin to see the first signs by December. If it is not there, we should be ruling it out pretty much over the entire mass range by the end of this year.
You're involved with a detector on the Large Hadron Collider at CERN called the CMS, the Compact Muon Solenoid. What is your responsibility for the CMS?
As the leader of the Higgs group, I have to be careful about two things. I should not find the Higgs boson if it is not there. And I should not lose the Higgs boson if it is there. Those are the two things. And the best I can do is to prepare very sharp tools, very sharp observables to search for the Higgs boson. What comes out of data is something that is nature's call. It is not in my hand. So I direct the international hunt for the Higgs boson with the CMS detector. My job is to basically devise the plan, work with teams of people on different searches of the Higgs boson, and arrive at a situation where we are today.
How many people are involved in those teams?
The experiment itself is a collaboration of 3,000 people, so that's what it takes to build the detector, keep it running in a good way. But the people who are actually in the analysis of or the search for the Higgs is about 500, 600 people.
Mm-hmm. Now there's another detector on the LHC with a similar, or actually a parallel and identical role and purpose.
Right, so there are two detectors, and CMS is one of them. Atlas is another. And these two detectors are there in order to check each other's results and findings.
Now, you've been given, you've taken on, or I don't know, given an additional role along with your responsibility as Director of Higgs Research for the CMS, but something involving both the CMS and the Atlas experiments.
Because these two detectors are similar, but they get different data, one can combine the results from both CMS and Atlas detectors. And I, along with Bill Murray from Rutherford Lab in UK, we lead this group of people which brings together results from the CMS experiment in Atlas.
Now there's a large number of people from the University of California involved in either one or the other of these detectors, is that true?
Yes, this is very much true. As a matter of fact, I think University of California, the physicists from University of California are some of the leaders, the main leaders of both the CMS and Atlas collaborations and detectors. I mean, so the scientific input and weight of UC physicists is substantial, and it's well recognized worldwide. The Higgs boson is a particle which is associated with the Higgs field, and that's a concept which is required in the Standard Model to understand how different kinds of particles get mass. Essentially, how everything in the universe gets mass is based on a conjecture, which is the presence of a Higgs field which permeates throughout the universe. And the basic quantum, the particle associated with that, is the Higgs boson. So if this conjecture is true, there must be a Higgs boson. And the importance of Higgs boson is that it is the particle that gives mass to everything in the universe. And without mass, for example, if electrons did not have mass, then there would be no hydrogen atom, because massless objects basically fly out at the speed of light. So you could not make the hydrogen atom. The electron would not go around a proton or be anywhere close in. So you couldn't make the hydrogen atom. You could not make any element. You could not make molecules, and thus you could not make life or mountains or anything else, galaxies, everything. So Higgs particle is all about our existence in this universe. Let's start with the Large Hadron Collider.
Okay.
It's a collider. It collides protons, as far as from our point of view, at very high energies. These collisions are then recorded by a camera. And CMS is one of the two large cameras. And when I say large, I mean about 14,000 tons in weight and many meters in dimension. And it's a camera. It's a complex camera which is made up of sub-layers, concentric layers of specialized cameras also. Some of them are made up of things that you're familiar with. For example, silicon wafers or pixels, which things that you have in your 10 megapixel camera, for example. And there's about 80,000 channels, and these channels or this detector or the camera elements react at about a few nanoseconds in terms of ability to trigger. But in a sense, it's a camera. And the purpose of this camera is to record this proton-proton collision and through it get a sense of what the universe was like in the very early moments after its creation.
How does it work? What are those, you talked about these concentric layers. Just peel the onion, so to speak, and explain it.
So again, one goes back to the proton-proton collisions. So in an interesting proton-proton collision, a whole bunch of particles fly out in the aftermath of the collision. And these are of two kinds. They're either charged particles or they are neutral, like photon is neutral, neutron is neutral. And our job is to reconstruct the momentum and energy of each of these particles, the charged particles and the neutral particles. The way we measure the trajectory of the charged particles is to make them dance in a magnetic field. So the inner part of the CMS detector has a very large magnetic field, 3.8 Tesla. And within that magnetic field are immersed these silicon strips or these pixels. And as the charged particle, which is produced in these proton collisions at the beam pipe, as it emerges outside, flies outside, it records, it deposits energy in the pixels or in the silicon strips. And that is recognized and transferred out. And those are what we call hits of a trajectory. And by reconstructing the hits, basically lining up the dots and connecting the dots, we can measure the curvature or the trajectory of the charged particles. And once we have that, there's a very simple relation from which we determine the momentum of that particle and the energy of these particles. Photons, with the neutral particles that are produced, they don't respond to magnetic field. So they just go straight through, completely unimpeded. And for them, we have very nicely put together a set of crystals, very expensive lead tungstate crystals. And these photons, at some point, will hit these crystals, and this will cause the crystal to glow. And we measure this glow, and from that glow, we can determine the energy of the photon which impinged on this crystal. And these crystals surround the entire interaction point. Yeah, just outside the tracking region where the silicon and the pixels are. And then we have such calorimeters, we call them, which record energy. This is why they're called calorimeters. And between these inner trackers and the outer calorimeters, almost every particle's energy can be measured, except one, which is the muon, which is a charged particle. It also curves in the magnetic field, but it doesn't deposit much energy. And so it basically streams through the entire detector. And it takes a lot of iron, which is placed in the periphery of the detector, for the muon to basically give up most of its energy. And in that process, as it's streamed through, there are these detectors which measure the trajectory of the muon. So once again, you get hits of the muons, but they are on the outer part of the detector. And you again connect the dots along with the hits that the muon gave in the inner tracking chamber. And by doing so, you can measure the curvature. And from that curvature, you can measure the momentum and energy of the muon. So it's all about measuring momentum and energy. Once you have all the momentum and energy of every particle that was produced, you can just play it back and arrive at that primordial collision of proton-proton that happens. And it is in that way that you get a window to the universe of the past. It is from these collisions that we hope to find interesting stuff.
Mm-hmm.
Now, what is interesting stuff? Well, interesting stuff is massive stuff, things which are very heavy. We are looking for particles which are, about the mass of a silver atom or a gold atom or higher. And E equals mc squared principle tells you that the heavier the object gets, the more juice, more energy is required to produce them. And so heavier things are, it's more difficult to produce. Sometimes you have glancing blows. Well, in that case, there isn't that much of a chat between the two colliding protons. But the fun stuff is when protons and protons collide head-on, or the partons, so the things which are inside them, when they collide head-on. That's when you get these heavy objects produced, because that's when there is largest amount of energy being transferred. To produce enough of these Higgs, these heavy objects, you need to have very high intensities of protons. And these days, what we have recorded is close to 200-300 trillion proton-proton collisions, of which only a handful would be interesting Higgs-like events from which we search for the Higgs boson.
We have a good picture, a good background on what the detectors, how they work, what the LHC is doing, getting protons to travel about just a little over 7 miles an hour, less than the speed of light.
Less than the speed of light.
Just 7 miles an hour.
Right.
When you compare 7 miles an hour to the speed of light, it's
nothing.
It's nothing. So we have these complicated machines creating and recording the collisions. And what is interesting is that it boils down to that very elegant and simple physics where you're just looking at momentum and energy to deduce what happened in the original collision. Can we look at some of these events, and you can show us what you're looking at in terms of the curvature of, say, a muon track or the deposit of energy from electrons?
The first thing is to show you where the collision occurred, and that's right here at the center. And what you see here is that the detectors all around the point where collisions happen. And in this picture, you see the inner part of the detector, and the outermost of which are these crystals, thousands of crystals of lead tungsten. These are the calorimeters. But silicon detectors are very close. They're hugging the point of collision in order to measure the trajectories better. But what you see here are different detectors responding to these particles which are flying out. And you can see that these particles have different curvatures. Some don't curve much at all. And the ones that curve are the ones which have lower momentum. This is a very basic electromagnetic rule that we teach in high school. So we measure the momentum of these particles, and in this case we know that they are muons because unlike any other particle, muons don't talk much. They just run through the detectors, pinging each of the detectors, depositing just a little bit of energy. And then it escapes right out of the detector. And as it does that, it records its presence. And you see that over here, each of these muons just basically ding, ding, ding goes through and records its presence in the muon chambers. Now you can measure from all these hits or dings, you can measure the momentum of these particles. And by measuring these momenta, you can go back in time and reconstruct, because energy and momentum are always conserved. You can go back and reconstruct the mass of the object or that process from which these 4 particles flew out. And if that is an object like the Higgs, then the mass of that object which blew up and produced these particles would be 200 GeV. All this is certain from measuring basically the trajectories and the nature of the particle which produced these hits. So after that long explanation, here is an example of what a Higgs would look like if it decayed into 2 photons. You can see that these are very energetic photons, and there is nothing else that is produced in association with it. And so that's one example, event display. Here is another example where a Higgs decayed into two massive bosons called the W bosons, which then promptly decayed into familiar things like the electron and muon and neutrinos. And here is the a good event where you see a muon of 32 GeV, so it's quite energetic. Here is the electromagnetic calorimeter, and you see this red spike. That's the energy recorded in the crystals, electromagnetic crystals. That's 34 GeV. And you can see that there is something missing. There is a lot of energy going this way, but not that much this way. And that's the missing energy. This is the way neutrinos flew out in this event. And by looking at all other features of this event, you could say that this is a candidate for a Higgs decaying into two massive particles, which then decay into electrons and muons. So this is another example of a Higgs event. But the one that I like the most, the one which is most satisfying, is the one where the Higgs decays in what we call the golden channels, or channels which are so obviously Higgs-like that nothing except one process apes that configuration. So the picture is very clear in this case. And here you have a Higgs boson which decays into two massive Z bosons. Okay, and the Z is about the size of a silver atom. So imagine Higgs decaying into two silver atoms, and these two silver atoms each decaying into two objects, two muons of opposite charge. So in the end, what you see is neither the Higgs nor the massive Z boson, but just what came out of them, which was stable, which are these four muons. And you measure its momentum, you know its mass, and you can compute correctly the mass of the Higgs boson candidate. So here is what a Higgs would look like in a convincing way.
Or the remnants of a Higgs decay.
Remnant of a Higgs decay.
And
this is the snapshot that we take.
And in this case, if this were borne out, the mass of the Higgs boson would be roughly twice the mass of the silver atom?
Yes, in this case. I'm not saying that this is the Higgs event. This is how you would very precisely determine what the mass of the Higgs boson is. At the rate at which we are colliding protons, there is a Higgs boson, you know, for around 140, 150 GeV, which is being produced and decaying every 20 seconds or so. So that sounds like a lot because we've been running for a year. But not every one of these Higgs particles, Higgs doesn't live very long. By the time it is born to the time that it dies, it barely travels, almost even at the speed of light, it barely travels the size of a proton, which is nothing, 10 to the minus 15 meters. But then it blows up. But in order to find this needle in the haystack of all other particles being produced, you have to look for a very characteristic signature in this Higgs boson popping off. Okay? And so very characteristic signature is very rare. Okay? But the important thing is that it is a very unique signature of the Higgs being produced in the collision. Okay? So that's why there are some event pictures which are interesting.
So why is it that an event like this, or perhaps the two photons being liberated, are not evidence of Higgs?
Well, in a sense, they are evidence, they're candidates for Higgs boson. But on basis of one or two events, you cannot determine that you have found the Higgs boson. And this is because of what we call background events. Basically, these are events which are produced in, or collisions. In the proton-proton collisions, you find all kinds of things that were yesterday's discovery. In 1984, the discovery of the W and the Z gauge bosons got a Nobel Prize to a whole bunch of people. Today, it's a nuisance for me because in certain configurations, proton-proton collisions produce Z bosons or the W bosons in configurations where at some extreme they can look just like the Higgs boson. But they are missing one thing. which is that Higgs boson always has a well-defined mass, while these other background objects are kind of randomly distributed. So when you search for a Higgs boson, what you will see is a distribution, a continuous distribution of background events, and over that you would see a peak or a sharp spike, and it is this spike that would tell you that you have found the Higgs boson, not just a single event display as I have just shown you.
So
and
you
this
can
see,
be getting W, W, and Z boson production at many different masses, but the Higgs is going to be somewhere in a definitive
exactly.
mass.
Either it's at 140 GeV or 250 GeV or 350 GeV. But if it is 140 GeV Higgs, all such events that I just showed you, apart from looking pretty, they will all pile up in a very narrow mass range, and they'll not populate rest of the stuff. Backgrounds, on the other hand, are distributed in some form which we actually understand because we know the physics of where they come from. So here is an example of how you would find the Higgs boson. This is again in the golden channel.
Right.
So it's golden because you reconstruct everything and there is very little background. And you see what is here on the x-axis is plotted is the mass of these 4 leptons or 4 muons that I reconstructed. As I showed you, I can measure that by measuring momentum and energy. And on the y-axis is just a counter. How many events did I find? And what you see here is that the background in purple is a continuous distribution. It is not confined to a certain mass. It's sometimes less, sometimes more, but it has a distribution which we understand. Okay, so that's what the background looks like.
So those
That's
those are Z
Those are
boson
ZZ,
creation events,
right.
and they can happen all across that range. And,
Yep.
and you think you're going to probably see more background of them happening in
At
this
some
mass, and every once in a while you might get a 600 GeV.
Right.
Okay.
Right.
Okay.
So it tells you that, what the distribution of background is. Now, signal, which is Higgs in this case, will not show up as a wide distribution like that. So for example, if the Higgs has a mass of 140 GeV, then it'll show up as a sharp spike over the purple, here in red, and that's what the Higgs would look like. If you saw enough of those guys, okay, then you got a discovery. If the Higgs were instead, say, 200 GeV, then it would show up on top of this purple background as this extra orangish looking enhancement. And then that's what you would say is the Higgs boson. If the Higgs were very heavy, like 350 GeV, it will again show up as an enhancement over a smoothly varying background. And that's how you find the Higgs.
It is not statistically significant yet.
It is
may
not.
never be. That
Yes.
might be it.
Yes.
There it is. Sorry, it's not significant.
Right.
However, to become significant, what greater degree, how many more events in that spike would you need to start going,
Yeah, well, there is a statistical rule for that.
Yeah.
It's a Poisson statistics, which is to say at what point can you rule out a fluctuation, just a random fluctuation causing what you have observed.
Yeah.
Now, my dream here would be to get, if I start getting 6 events and 1 background or 1.5 background predicted, then I'm calling people. Then it's getting very interesting.
Now there's a bit of nuance here. This is at this mass, at this energy. Now there are other possibilities of a lighter mass Higgs boson. Can we go back to the
Right.
Photon event?
So in all these pictures, the story is the same. There is background. Sometimes the background is small, as in the golden channels, when Higgs decays into 2Z bosons. And in some cases, like Higgs goes to 2 photons, beautiful events. But here the background is much larger because nature has processes which are not Higgs. Very, very standard model, very pedestrian, very boring. But it's got enough of them that when you combine them all, they add up as large backgrounds.
Yeah. So
and that's what you see here.
So it's almost cautionary at this point for people to look at this and go, yeah, there are some events that are above background, but the magnitude of the events above background, they kind of look like the jitters in the background.
Yeah.
They could just be a jitter.
More data will smooth out these jitters. The Higgs signal, if there is Higgs, will be from these same two photons. But again, background is everywhere in mass, but the Higgs is a very narrow signal. So it will show up as a spike or an excess over a smooth, continuous distribution of events from background. The physics that we know, the standard model that we know, predicts almost everything about the Higgs boson, except one thing, which is its mass. And so you have to hunt for the Higgs boson at all masses. We start off by making a model where we say there is no Higgs. If there is no Higgs, what should our data look like? Okay? And from that, what could we derive? And so what this graph shows you here is a summary of our findings. So what you see here on the horizontal axis is the mass of the Higgs boson. And on the y-axis is what we can say about where the Higgs could be and where the Higgs could not be at a 95% confidence level, which is that if that 95 or 100 times, I'm sure of what I'm telling you, what I'm talking about, and where the Higgs is or whether the Higgs is not. And so what you see here in this dashed curve as a function of mass is our expectation of what we can say about the production rate of the Higgs boson. This is all based on simulations. Okay? You do many, many simulations. That red line at 1 tells you what the standard model says the production rate for the Higgs boson should be. And so whenever the dashed curve lies below the red line, one can potentially eliminate the presence of the Higgs boson. Of course, whenever you do measurements, there are measurement errors, there are uncertainties. And so what you do is you characterize those uncertainties in terms of this green and yellow region, which is basically the corridor of uncertainty. So I'm trying to find something new, but my base model is that there is nothing new. There is no Higgs boson. There is everything else which is in the standard model. There are W's and Z's and jets and B's and taus and muons, but there's no Higgs boson. Now, on basis of all this that are produced in proton-proton collisions, what should I expect to see? Okay, so that's my model, and what my expectation is that dashed curve.
Yeah.
Okay. If there is no Higgs boson or Higgs boson-like object, then my data would lie right on top of the dashed line because there is no Higgs boson, so my data must look like my model. But if there is the Higgs boson, then there will be a difference between data and my model because my model says there is no Higgs boson, and that curve is on basis of that. But data, if it truly contains Higgs boson, will ride on top of my expectation and depart substantially both from the dashed curve, the corridor of uncertainty, and if it lies outside that, that's when the bells start ringing. And what you see here in data is that for majority of the time, what we observe lies below the red line. And so we have determined that the Higgs boson at 95% confidence level cannot be in that region. And so that's the most important finding, that effectively 90% of where the Higgs boson could be, remember we don't know where it could be, but that mass range is eliminated at 95% confidence level today, with higher confidence level tomorrow as we take more data. I mean, it's an endless game of exclusion. So now the Higgs boson is basically, on basis of plots like these, we can conclude that the Higgs boson, if it exists, must be between 114 and 145. So now the focus is reduced to a very small mass range in Higgs, between 115 to 145 GeV. And as we take more data, we will be searching for the Higgs boson here. If there is a Higgs boson, okay, and as an experimentalist, I don't know whether it is there or not. I just search for it. But if it is there, then what I will begin to see in data already are excesses. I would see many more of them than what I predict on basis of my knowledge of all the backgrounds, the imposters, the wannabes, the false prophets. I will begin to see an excess. And it's that excess, when it becomes statistically significant, would be the basis of claiming a discovery of the Higgs boson. Likewise, if the Higgs boson doesn't exist, then even as we continue to take more data, the number of background events that I predict would increase because I added more data. But I would see no excess, no statistically significant excess. And that would be the way by which I would eliminate the case of Higgs of that mass.
We call it the hunt for the Higgs or search for the Higgs. At the same time, it's truly excluding where it can't be. Right now, there's still a chance, and you want to get that down to nothing. So if there is an indication of a mass that you can clearly say, well, we know it's not here, and we know it's not there.
Look, I'm doing much better than the weatherman, but I'm far more ambitious than that. The probabilities of my statements have to be, much more than the poor weathermen. Actually, the San Diego weathermen do okay. It's sunny all the time. I have to have two plans. One is to find it if it is there and quantify it. That's the 5 sigma rule. And the other is that if it is not there, then I have to quantify that too in a statistical term. Right now I'm saying it's not between 145 to 450 or 460 at 95% confidence level, which means there's a 5 chance out of 100 that my statement is wrong. Okay, little self-respect. I would like to do better. I would like to have 1 chance in 100, 1 chance in 1,000, or 1 chance in 100,000 that I'm wrong about what I said. So when you believe me that the Higgs boson doesn't exist, you have to trust me a little bit right now, because it says 5 times of 100 I could be wrong. And I want to remove that element of trust and keep it objective, get it to a point where I am sure 1 part in 100,000.
Considering how much data you have so far and what you've excluded, is there a range that you think that something might emerge in a range of subsequent data to come yet? Is it this doubling of data? We'll have a much more clear picture, or maybe even a definitive picture, or is it going to be next year and running 2012?
Well, Mick Jagger once said, too much is never enough. So in terms of luminosity, we continue to strive, continue to go as fast as we can. This is science. I don't know what the Higgs mass is. I'm probing for it. One thing I do know is that as the Higgs boson becomes lighter, the background grows. Okay, there's more background to deal with. And so if the Higgs is heavier, it's easier to find in some sense, and if it is lighter, then it will take more time. So if the Higgs is 114 GeV or 115 GeV, we may have some tantalizing evidence by this year, but not anywhere close to the kind of burden of proof that we need to show, the 5 sigma rule. That will have to be next year. And next year we plan to take at least twice as much data as we would have recorded this year. So, the machine keeps doubling, and it's all because we don't know where the Higgs boson is, and we want to make sure that we have enough data that we can rule out the whole thing or find it.
But there is something interesting going on in this area.
114 to 145,
that in previous theory or model and prediction, it has been indicated as a possibility of where the Higgs might exist.
Yeah, so we have done several experiments in the past, and one can try to infer from those measurements, with help of theory, where the Higgs boson could be. Unfortunately, from that data, one can only learn about Higgs in a very diluted way. But if you take all this existing measurements, some of which too I have contributed to in the past, also at CERN, you get a picture of Higgs boson mass, which is consistent with the range that we have cornered the Higgs boson in right now. So it could well be that the Higgs is there, and And this weak hint that we had of what the Higgs mass would be borne out. On the other hand, it could well be that there's no Higgs.
That's it. That's nature has given you to work with, and you're going to keep getting the same results or the same evidence.
Right.
Now let's if we can reflect a bit. When the first collisions, the 7 TeV collisions, commenced back in March 30th, 2010, you said something to the effect that the baby is born and it's just learning to walk, but this will be a marathon. Now, obviously the baby has grown and has learned to run, and quite well. How are you feeling? Has the baby hit its pace, or can you hear the stadium and the crowd roaring like the marathoner in the Olympics? You know, they have to run through the city and then there it is. How do you feel about that? Or is there a way to go yet?
I wanted to be conservative and careful. I said the Higgs search will be a marathon because we won't be producing enough Higgs bosons through the detector quickly enough. But that marathon, because of the performance of the LHC machine, has now become a sprint. So we are sprinting. The only problem is we don't know where the finish line is. Okay? But it is not a marathon. It's not a slow run. It's a sprint, and we will continue to do that until we see the finish line. So I'm not thinking of the stadium. I'm not thinking of the crowds. I'm just sprinting and trying to get to a place where either I can completely rule out the Higgs boson, or if it is there, find it in style.
The mission of the CMS detector has been described as this. It is designed to help answer questions such as, what is the universe really made of, and what forces act within it, and what gives everything substance? Now, when you and I started our chronicle of your work with this search about a year ago, or maybe longer, you described to me an essential and very early inspiration for you that comes from a divergent but curiously parallel source of thought on the subject of existence, and that's the Rig Veda, an ancient Sanskrit text, also known as the Song of Creation, and it's over 3,500 years old, I think. Tell us your early experience of the Rig Veda, how you came upon it, and how this influenced you and what inspiration you drew and draw from those philosophers of so long ago.
Yeah, when I was a young kid growing up in India, my mother, she knows Sanskrit. She's a scholar in Sanskrit, and so she taught us Sanskrit, and the sages, they wrote the code of conduct, their wanderings, their philosophies in Sanskrit. And one of them was the Rig Veda, which is one of the primary documents from thousands of years ago. The Song of Creation is one of the early songs in this book, and it had a profound impact on me. It is almost a jarring influence. Because it was a record of what the sages saw thousands of years ago, looking up at the sky. And rather than putting out preconceived answers, I mean, they just basically wrote a song, which is a series of questions, almost beckoning the civilization later on to find ways to answer those questions. It was a telegram from 3,000 years ago that I was reading when I read the Song of Creation. And I think close to that, I decided that I'm going to do science, and in particular, I'm going to be an experimental particle physicist. And today, when I investigate where mass comes from, what caused the universe to be in the form that it is, I see this as a privilege to be in a position to have the scientific tools with which to answer these ancient questions, these calls from thousands of years ago on how the universe began.
Indeed, it is in the frontispiece of your dissertation. Here's a passage, and this one in particular resonates to me. Darkness there was, at first concealed in darkness. This was all undiscriminated chaos. All that existed then was void and formless. By the great power was born that unit.
One of the reasons I'm doing particle physics is because of that song. And it moved me, it means a lot to me, and I remember it every day. And it drives me, it propels me towards to answer some of these questions, like, what is the origin of mass? We finally have the tools to understand these questions or explain in not a speculative way, but in a very objective way, why we exist. If there isn't the Higgs field, of which Higgs boson is a carrier or a quantum, then we do not have a way of explaining the universe we live in. Because without such a field, we would not have a theory on how particles get mass, why the electron has the mass that it does, why is the neutrino have so little mass, why is the top quark, the mass of a gold nucleus. We would not know any of these things. In the theory that we have, without the Higgs boson, everything would be massless. The electron, the quarks, everything. So no chance of forming an atom, because you couldn't get a proton and electron to hang around with each other. They would just fly off, because objects which have no mass, Einstein tells you, they will move at the speed of light. So there would be no atoms. There would be no molecules. There won't be any chemistry. There cannot be flowers. There cannot be us. There will be nothing. I mean, it would be a very barren world of light that we would live in.
Or, in another way of saying it, all would be void and formless and undiscriminated chaos.
Exactly. But this is why I say there's a reason why I remember these things every day. But these are speculations, and I don't want to go into metaphysical aspects of these things. But the pleasure, that's the important thing, is that I have the privilege, I and many of my colleagues, we have the privilege to answer these questions of the civilization, by ourselves. And there will be a day when I will know the answer and keep it with me before telling the world. No more than 24 hours. But there will be a moment when I would know what the answer is. And just the thought is very exciting.